We have mapped the human brain down to the nanometer. We can trace the exact molecular cascade where synapses compete for survival, right down to the specific protein bottlenecks inside an individual endosome. Yet, when we design drugs to fix these exact microscopic mechanisms, they consistently fail to stop clinical decline in broad patient populations. The biology mapping the synaptic production floor is completely accurate. But assuming that this specific production floor is the primary therapeutic target for everyone is a structural error in how we view the disease. Having a perfectly engineered tool is useless if we are repairing the wrong machine inside the patient's brain. The theory of constraints treats the brain like a complex manufacturing facility. It requires raw material supply, energy processing, waste removal, and synaptic production. In this multi-bottleneck system, the true constraint is highly specific to the individual and changes over time. If a patient's actual bottleneck sits upstream in the supply chain, fixing the downstream synaptic network will produce zero clinical improvement. The synapse is starved before the repaired mechanism can even activate. To locate the true drivers of Alzheimer's pathology, we must step back from the synapse and map the entire upstream supply chain. The first critical upstream system is the cerebrovascular network. The blood-brain barrier acts as the strict receiving gate for oxygen, glucose, and signaling molecules. Clinical data shows that midlife hypertension roughly doubles the risk of developing Alzheimer's decades later. This is a supply chain failure, effectively choking off raw materials at the source. We can track this deterioration in real time. Pericyte-derived biomarkers like SPGDFR-beta reveal blood-brain barrier breakdown in midlife, years before any conventional amyloid accumulation or memory loss begins. This matters because the mechanics of synaptic competition require immense trophic and metabolic resources. When vascular delivery degrades, the resource pool shrinks. Synapses are forced to fight over a diminishing supply, accelerating a competitive death spiral, completely independently of any specific protein misfolding. For patients carrying vascular comorbidities, their cognitive decline originates as a supply chain collapse. Treating them with targeted endosomal drugs is operationally futile. Delivering raw materials is only the first step. The brain must also process them. Brain tissue can develop severe insulin resistance, disrupting the signaling receptors required to pull glucose into the cell. This chart illustrates the quantitative metabolic failure in these patients. We observe a 25% reduction in hippocampal glucose metabolism in Alzheimer's patients, aligning exactly with the data showing that type 2 diabetes doubles the risk for the disease. When this energy substrate is compromised, the brain's metabolic sensors misread the environment. The system registers a severe resource scarcity, prematurely tightening the rules of synaptic survival and culling healthy connections. Simultaneously, this specific breakdown in insulin signaling actively increases amyloid beta production and tau phosphorylation through entirely separate pathways. Roughly 40% of Alzheimer's patients present with significant metabolic dysfunction. For this population, their baseline glucose metabolism must be corrected before any downstream interventions can succeed. As the factory operates, it generates toxic byproducts. The brain manages this through the glymphatic network, a system of perivascular channels that physically flushes neurotoxic metabolites out into the plasma during deep, slow-wave sleep.
Sleep disruption destroys this cycle. When the glymphatic drain is blocked, the brain's thermodynamic sinks fill with amyloid, even if baseline production rates are perfectly normal. Beyond internal maintenance, the system is highly sensitive to external environmental hazards, specifically systemic infectious burdens like HSV-1 and severe gut dysbiosis. Gut permeability allows bacterial endotoxins to enter systemic circulation and cross a degraded blood-brain barrier. Once inside, they lock the brain's microglia into a state of chronic inflammation. Amyloid beta is a conserved antimicrobial peptide. In a highly inflamed environment, the brain manufactures amyloid on purpose as a legitimate immune defense against these invaders. This creates a catastrophic loop. Chronic systemic inflammation forces the brain to hyperproduce toxic waste, while simultaneous sleep disruption shuts down the exact biological plumbing needed to remove it. The detailed mapping of endosomal bottlenecks and synaptic competition is clinically correct, but only if all of these upstream supply and maintenance systems are fully functional. Autopsy data consistently reveals a secondary complication: parallel production lines. The majority of clinical dementia cases do not isolate to a single pathway. They feature multiple, entirely distinct pathologies running concurrently. For instance, TDP-43 pathology is present in over a third of people past age 85. It accelerates cognitive decline through its own dedicated mechanisms, completely bypassing the amyloid cascade. Similarly, microinfarcts inflict pure structural damage. Maintaining perfectly healthy cortical synapses yields no benefit if the physical white matter wiring connecting those regions is severed. For older populations, the true constraint is the sheer multiplicity of failure modes. Correcting one molecular cascade cannot restore function if parallel structural networks have already collapsed. Because the rate-limiting step shifts based on the individual, monolithic treatment approaches fail. A 50-year-old ApoE4 carrier requires an endosomal intervention, whereas a diabetic 60-year-old needs metabolic interventions to restore energy. Therapies must match the patient's specific constraint. This multi-system variance is why the BCG vaccine, and specifically its LL37 peptide component, represents such a compelling therapeutic candidate. Upstream, BCG induces trained immunity, dramatically reducing systemic inflammation. Downstream, the LL37 peptide acts directly on the production floor, chaperoning amyloid monomers and restoring microglial selectivity. It does not cure insulin resistance or reverse vascular damage. Its value lies in its unique immunological footprint, capable of covering multiple failing subsystems simultaneously. To actually operationalize any of these treatments, the field requires one final component: a real-time diagnostic dashboard capable of identifying the specific, individualized bottleneck. This requires a highly composite biomarker panel, tracking SPDGFR-beta for vascular integrity, FDG PET scans for metabolic function, and biomarkers for copathologies like TDP-43. Managing neurodegeneration without this multi-layered panel is equivalent to managing a complex manufacturing crisis by guessing which machine on the floor is actually broken. Alzheimer's is fundamentally a systems engineering problem. Until we build the diagnostic infrastructure to monitor the entire cognitive value stream, perfectly engineered molecular interventions will continue to fail.